Okay, it's probably the time to start. Today, our distinguished speaker is Akardy Tsetlin from Imperial College of London. He will tell us on his joint work with Simon John Bibikari and others on one-on-one corrections from quantum M2 branes. So please, Arkady Alexandrovich.
Okay, thank you very much for the invitation. So I will talk about, indeed, the title is there. So the main aims in general, of sort of motivation for this talk, I guess the general motivation is to try to understand gauge theories at any values of coupling, and there was a lot of recent work in the context of ADS-CFT, which went into that direction. At the same time, through ADS-CFT, gauge theories are related to string theory. So that gives also non-trivial information about string theory in curved background. So these are two main aims, and they're kind of related. And one main tool which was used in the past 15 years to shed light on gauge theories on supersymmetric gauge theory in the context of maximally supersymmetric ADS-CFT correspondence was integrability, which allows to find essentially anomalous dimensions at leading order at large n, in the case of SUN group, and any value of string tension or gauge coupling. The question, which is kind of the focus of this talk, is how we can go beyond large n limit. So in particular, we would like to compute corrections to dimensions of primary operators in 1 over n expansion, subleading terms in 1 over n expansion. So I will explain what that all means, but let me again to rephrase what I just said. So in quantum field theory, one of the major problems is how they go beyond perturbation theory. And in, say, SUN super Young-Mills theory, or Young-Mills theory, we have two parameters in 't Hooft expansion, in large n expansion, which is n and lambda, which is product of Young-Mills coupling squared times n. So for fixed lambda and expanding large n, observables have, for example, free energy on a sphere has expansion which starts with leading planar term, which is like n squared, and then there are subleading terms in 1 over n. So in general, we'd like to know what the structure of these subleading terms as functions of 't Hooft coupling. And there was a remarkable progress done in the context of superconformal theories, trying to compute these functions of lambda corrections in different particular observables using combination of different methods, and in particular integrability, which I just mentioned, which is restricted to leading order in large n. Then there is localization, but it's also restricted to particular supersymmetric observables like free energy or Wilson loops. And localization allows to get exact expressions for in terms of Young-Mills coupling and n. And then there is also bootstrap, which also gives important constraints, but it's also limited to some general principles and symmetries and requires extra input. So there are different methods, but not much was actually done about 1 over n corrections explicitly. So anomalous dimensions of operators in, say, super Young-Mills theory, or I would later discuss three-dimensional Chern-Simons theories, so-called ABJM theory, they have this kind of expansion where the planar part is just function of lambda, and then there are 1 over n squared corrections. So delta zero is controlled by integrability, and that weak coupling is just a series in lambda. So weak coupling means, by weak coupling, I understand small lambda expansion. While at strong coupling, depending on which operators we consider, for long operators, it goes as square root of lambda, and for short operators as fourth root of lambda, and then there are a series of 1 over square root of lambda corrections. So this we know from string side, but also we know now from integrability, we know how delta zero goes as weak coupling and strong coupling in principle. But how to compute subleading corrections at delta one, that's the focus. And here, little is known even at weak coupling. So, for example, in N=4 theory, in N=4 Young-Mills theory, what is known is that for the cusp anomalous dimension, or dimension of the operator, which has, say, two scalars and many covariant derivatives along some plus direction, some direction in some plane. So it's a long operator with large spin, and if we look at the coefficient of log s in its anomalous dimension, which is 2 plus s, well, 2 is irrelevant, s is large. So this function f of lambda n is what's called cusp anomalous dimension, and at weak coupling, it's essentially powers of lambda, and non-planar correction first appears at order lambda 4. So these are some coefficients, they don't matter, but so non-planar corrections start only at high enough order, and that's essentially what is known. And similar happens for short operator like Kanishi operator. Also, non-planar correction starts at order at for loop order at weak coupling. So at weak coupling, so essentially this seems to be general conclusion that at weak coupling, this leading the coefficient of 1 over n squared term, it starts at fourth loop order. But what we should expect at strong coupling? That's the question which I'd like to address in this talk. What's the behavior of this non-planar correction at strong coupling? So it should be some lambda in some power leading, again, it's leading asymptotics of this function delta 1 at large lambda. So it's some power lambda. So there's no known way at the moment to predict this power p in N=4 super Young-Mills theory. So essentially, the reason for that is that computing non-planar correction requires doing one loop string theory, one loop computation for string theory in ADS5S5, which is dual to N=4 theory. And this computation appears to be challenging. We don't really understand how to. Well, it could be done, but probably could be done, but it's just a technical problem which is not well understood at the moment, partly because description of this string theory in ADS5S5 requires Green-Schwarz formalism, and in that formalism, computing loop corrections is not straightforward, but in any formalism, it's not straightforward. So remarkably, and that's the main subject of my talk, progress can be done in three-dimensional ABJM gauge theory, which is Chern-Simons theory plus method, supersymmetric Chern-Simons theory plus method, which I'll describe later. So what happens in this theory, there is an extra tool which we have to capture these 1 over n corrections, and that's we can think of, instead of strings, in terms of membranes, and the membranes will be propagating in this space, which is ADS4S7 over ZK, which I will describe. And here, in fact, just quantizing semiclassically M2 brane instead of string, we can capture subleading in n corrections, as I'll explain. So that'll be the main subject of the talk. Yeah, feel free to ask questions if I may carry on without stopping if you don't ask questions. But yeah, I'm happy to answer questions in the process. So just to set up the stage why we talk about membranes, let's recall where this whole story about membranes come from. It's 11-dimensional supergravity. In 11-dimensional supergravity, there is a classical solution, which is like supersymmetric half BPS solution, which is M2 brane. And its near horizon limit is ADS4 times S7. So that's the metric. And the scale of this space is related to number of membranes or the charge of the membrane. So you, by the same way how we do this for D3 branes, we can think of many M2 branes put together, and there is some dual theory which describes multiple membranes which live at the boundary of this ADS4 space. So boundary is three-dimensional, membrane has three-dimensional weld volume, and scale of the space is related to n, number of membrane. So that's a kind of heuristic picture suggested by the existence of this half BPS solution. But then one can also think of what kind of object this membrane is by itself. So for that, one could look at collective coordinates and construct the action for this membrane. Just what one can do for a string, for a long string, say, looking at its small fluctuations. But in fact, the history of this subject is such that the action for this membrane, for supermembrane, was constructed before this M2 brane solution was discovered, but just by analogy with Green-Schwarz action in string theory, in 10-dimensional string theory. So this membrane action, it essentially has volume term or usual term which we have for the action, for the string, like Nambu string. Then it's super generalized, so you have also fermions, which are thetas, and then there is a coupling to three-form field, which is present in 11-dimensional supergravity. This three-form C3, which is it's the fundamental field of 11-dimensional supergravity. So that's it could be non-zero in the background. So in addition to the metric, we have C3, and membrane is propagating in this background. And that's roughly how its action looks like. So the important parameter here is the tension of membrane, which is related to Planck constant in 11 dimensions, which is just expressed, Planck constant is just scale of kappa 11, of Newton's constant in 11 dimensions. So the most important piece of information is that this 11-dimensional supergravity action, if we compactify it in a circle, we get the action of type 2A supergravity. And in the way how this compactification can be done, or dimensional reduction, you can write the metric such that here 11-dimensional metric contains part which is 10-dimensional string frame metric, times the scale which happens to be dilaton in 10-dimensional action. So this is 11-dimensional coordinate, which is assumed to be compactified in a circle of radius R11. And then the parameters are related, so the dilaton is related to string coupling. So essentially, the string coupling is related to radius of this 11th dimension, and kappa 10 will be related to string coupling and string tension. So that's a key point, that if we start with this membrane action, in fact, and do double dimensional reduction, namely, we compactify this 11-dimensional coordinate, plus we assume membrane has cylindrical form. So it has one of the two spatial coordinates of membrane is a circle as well. So it's like a long string, but expanded in one extra circle. So if we compactify on that circle as well, this is what's called double dimensional reduction. The membrane action becomes just superstring action, propagating in the corresponding 10-dimensional background. So in that sense, one could conjecture that theory of string theory at strong coupling should be somehow related to theory of quantum membranes. So strong coupling means that this radius of 11 dimension is no longer small, but finite, and then it encodes the string coupling. So that's essentially the picture which emerged in mid-90s, and that's what was called essentially one of the ideas behind this is what's called M theory, which is not completely clear what, but it should be somehow related to theory of quantum membranes. Now, membrane is a strange object. so bosonic membrane action, which was discussed already by Dirac. So it has this volume action, it has diffeomorphisms, but it has too many components of this metric, GAB, but only 3 diffeomorphisms. So it has six components of the metric, but 3 diffeomorphisms. So compared to string action, like Nambu action, where you have 2 diffeomorphisms and 3 non-trivial components of the metric, you cannot actually gauge fix here all the components of the metric completely. So you don't know how to solve this theory in terms of, say, free fields. It's highly nonlinear theory, and in general, it's non-normalizable. So yeah, if you expand, for example, the square root of determinant, you'll get all sorts of nonlinear terms. For example, we can fix static gauge and expand near long membrane. We'll get high and high derivatives, terms with many derivatives of x, of coordinates x. So it's formally non-normalizable, and trying to quantize this theory is also, there is an issue of what's called no mass gap in the spectrum of small membranes, etc. So supermembrane may be better defined at the quantum level, and in fact, it is one loop finite as a 3-dimensional theory. Just by this is kind of simple fact of dimensional analysis that in 3-dimensional theory, which has the diffeomorphism invariance, you will not have, or gauge invariance, you will not have log divergences just on dimensional grounds. So there are no log divergences at one loop, but there could be 2 loop divergences, etc. So it will not be randomizable at higher order, at higher loop orders a priori. But as we will see, there are indications that actually supermembrane may be effectively finite theory if indeed if it's defined in some special way to match dual gauge theory, as I'll discuss. So the expansion which I will be focused on is just semiclassical expansion. So instead of trying to quantize this membrane exactly, what we'll do is to look at particular classical solution which has some proper interpretation on gauge theory side, and expand membrane action near that classical solution. So that's what is called semiclassical expansion near saddle point, or a particular saddle point. Important point is that this induced metric should be non-degenerative when expanded near this classical solution. Then there's no problem of quantizing this membrane action, just fixing static gauge. Static gauge means you fix 3 of the target space coordinates to be equal to world volume coordinates, 3 world volume coordinates, and then the action becomes just expansion and derivatives of the transverse coordinates to the surface. So that's how again, the action looks like, expanded in square root of g. The bosonic part, the volume part, will be expanded. So this is bosonic part. Volume part will be expanded in derivative of x. For example, one loop approximation will be just 2 derivatives, dx term. Then there is also Verzumina term, which needs to be also expanded near classical solution. And then there's a fermionic term, which will be focusing just on one loop approximation, so it's just quadratic in thetas. So here I wrote it very explicitly, but it looks kind of complicated, but structurally it's very simple. It's just quadratic term in thetas with some covariant derivative, which depends on 4-foron flux, the strength of this C3 field, which in general will be, which is non-zero in ADS 4S7 background, which we'll be considering. So then you integrate over x and theta to one loop order. It just means this quadratic approximation. So there will be exponent of the classical action of the membrane wrapped on some surface. And then there will be one loop prefactor, which will just given by determinants of these fluctuation operators near that given surface of the membrane surface. So it's the same semi-classical approximation which you do in any gauge theory or string theory. So here one can do this for the membrane. And several general points is that we're not going to sum over membrane topologies. So in fact, we just look at one particular saddle, one particular classical solution, and study these loop corrections in inverse membrane tension. So parameter here is membrane tension, T2, and we expand in this inverse tension of membrane. Just like what we do when do alpha prime expansion in string theory, we expand in inverse tension of membrane. So we just look, we don't sum our topologies, but what will happen is that this semi-classical expansion for a membrane near single saddle will encode dependence on string coupling to all orders, because string coupling enters through this radius of 11th dimension of this 11-dimensional background in which membrane propagates. So the background metric, in fact, knows about string coupling of the string theory, which is obtained by, which corresponds to this membrane, to this 11-dimensional background upon dimensional reduction. So if we assume the membrane, so I'm assuming the membrane, always assuming the membrane has topology, which is two-dimensional surface times a circle. So membrane always has circular dimension, and that circular dimension will be identified with 11th dimension of 11-dimensional background to have this 10-dimensional string theory limit, to have this interpretation in terms of string theory and be able to connect to string theory. So then what happens is that for that membrane, if you do Kaluza-Klein expansion in this circular dimension of the membrane, what we will get an action of a string, which is obtained by double dimensional reduction. Namely, we just have zero modes, which will be string theory modes, but then there will be a tower of massive two-dimensional fields living in this effective two-dimensional theory, and we write three-dimensional theory as two-dimensional one if we have as one circle, plus all infinite tower of modes which are massive. The masses of these modes will go as 1 over 11-dimensional circle, and they will be 11-dimensional circle is related to string tension and string coupling. So it effectively means that the membrane action will be looking like string action plus infinite tower of massive fields, masses of which are related to string coupling. So that means string coupling effects, so loops in string theory will be encoded just in this three-dimensional theory. So if we integrate this tower of massive modes, we'll get some effective non-local theory on two-dimensional surface. So it's like saying that in some sense it might be related to the idea of resumming all string loops in terms of some effective string action on a sphere with insertion of handle operators somehow. So this similar idea, when you try to encode all loops, all string loops, all sums over high genus surfaces in string theory as some effective two-dimensional theory, which may be non-local, but contains all the effects of this string coupling dependence. So effectively, that's what happens here, that we have a membrane action, which is three-dimensional, but this extra dependence on coupling comes through 11-dimensional background, or radius of 11 dimensions. So we'll see explicitly how that happens in the example of this ADS4S7 over ZK, which I'll explain what that means, which is due to ABJM theory. So what is ABJM theory? This is an attempt to understand what is the theory on multiple M2 branes. So if we put many D3 branes together, we get N equal 4 to Young-Mills theory at low energies. So the same question for membranes happens to be less obvious. Answer to the same question is less obvious. And what happens is that to get a weakly coupled theory on multiple membranes, one needs to consider not just multiple M2 branes put together in flat space, but one needs to take an orbifold. So we start with 11-dimensional space, say flat space. We take the 3 dimensions, which correspond to kind of world volume of the membrane, being the usual 3-dimensional Minkowski space, but then we take an orbifold of the remaining R8, dividing by ZK action. So this orbifold is non-singular, and the only reason is for this orbifold is to introduce an extra parameter k integer, which will play the role effectively as a parameter which you can tune. If you take k very large, that will be a weakly coupled theory. So I will not explain this in detail, but the main point is that if k equal 1, that's a singular, well, this is strong coupling limit of that theory. If k equal 1 will be just a multiple theory of membranes which correspond to this ADS4S7 geometry, which I mentioned earlier, near horizon geometry of multiple M2 branes. But having this ZK leads to a theory which has n equal 8, n equal 6 supersymmetry only, not n equal 8. N equal 8 is restored at k equal 1. So n equal 6 superconformal theory, which is found in this way, it has a gauge group U at level kn and similar at minus level kn. What that really means is that you have two Chern-Simons theories with level k, k and minus k, coupled to certain matter, which is 4 scalars and 4 fermions in a joint in bifundamental representation of these two groups. And there is some interaction potential for scalars, and there is a interaction between fermions and scalars. So the theory is n equals 6 supersymmetric 3-dimensional theory, superconformal. It's UV finite theory, superconformal, with explicit structure which admits weak coupling limit if k is large. So k plays the role of inverse of Yang-Mills coupling. It appears in front of these gauge Chern-Simons terms, which are analogs of Yang-Mills kinetic term in this context. So essentially, k is like 1 over G Yang-Mills, and that means there is a same analogous Toft limit. So the Toft coupling will be n over k here. So the usual Toft coupling is n times G squared Yang-Mills. So here it will be n divided by k. So this is analog of Toft limit will be large n. Again, n is number of membranes or rank of UN group, and large k, such that lambda n over k is fixed. So this will be, this Toft limit will be string theory limit, which is due to type 2A superstring theory on ADS4 CP3. So why CP3, we'll see in a second, but yeah, so that's the main claim of this this ABJM paper, that considering this particular theory in Toft expansion, the dual theory should be superstring on this space. So 10-dimensional space like this. Now, what happens at finite k? So if we fix k and take n large, so clearly that will correspond to very large lambda. And that will be non-perturbative regime from the point of view of this 3-dimensional gauge theory. So here the claim is that this is M theory regime in the sense that we kind of take the radius of 11th dimension, not small now, but any radius. It could be large, small, it's fixed. So that in that limit, the theory is due to ADS4S7 divided by ZK. And again, this factor comes from the original construction on the orbifold, on this multiple membrane on orbifold. So we just take this for granted that that should be due to this ABJM theory. So the metric of this space is can be written very explicitly. So this orbifold, it's a very simple thing in this context. So if we consider Hopf vibration of S7, writing it as CP3 with an extra circle, and this A here is a function of these CP3 coordinates as written here. So the HRS is metric on CP3 and A is related to it. So the important point, there is a circle which is compactified with angle 2 pi or 2 pi over k in the original orbifold, but we can take this 1 over k squared out. So then phi is the usual periodic angle. If k is 1, this is usual S7, but if k is not 1, if this radius is not equal, is less than 1, that becomes this S7 over zk. So that's explicit metric of the space, and that's what is claimed to be dual. This background, these membranes in this background is a dual to M theory in this background, is dual to ABJM theory at the boundary of this ADS4 space. So string limit, as I mentioned, correspond to large K because lambda is fixed in this limit, and then we just end up with ADS4 and CP3, this space. So then there is a relation between string coupling and parameters of ABJM theory, lambda and n. And the most important relation is this, that 1 over k squared, so k again is this integer which is level of Chern-Simons theory, or lambda over n squared. It's related to this combination of string coupling and string tension, and again, string tension is square root of lambda, in the dual string theory in 10 dimensions. So that's the combination which is related to 1 over k. So in 11 dimensions, k is, so from 11-dimensional point of view, n and k are related to the scale of the space, and k is essentially the radius of this 11 dimension. So these are interpretations. Now, on string side, this is string coupling and string tension. That's the two parameters. So the claim then is that the operators in this superconformal theory are due to membranes, membrane states in that space. So that's the main postulate, that the main claim. Just like in string theory, dimensions of operators are related to energy of strings in, say, ADS5. So here, it will be energy of membranes in ADS4 related to dimensions of dual operators at the boundary of ADS4 in ABJM theory. So M theory expansion will be expansion in the large L scale of this space compared to Planck scale, and that is large for n large and any fixed n, k. So that's this relation. L is related to n times k and Planck length. So if k is fixed and large, that means L is much bigger than L Planck. And so expansion of observables in that limit will be like this. So membrane tension, effective membrane tension is just 1 over Planck length cube times the scale of the space. So that will be dimensionless combination. And this dimensionless tension, effective tension, is just n times k. This is what was in the context of string theory, that was like square root of lambda. So here the M theory analog of membrane tension is n times k. And that should be large for membrane perturbation theory. So semiclassical expansion of membrane applies when this parameter is large. So clearly for fixed k, n large, that condition is satisfied. So expansion in inverse membrane tension will look like this. It will be functions of k, with k is fixed, and then there will be corrections in inverse tension. So the main point is that if k is fixed and we're expanding in tension, we capture 1 over n corrections. So in also expansion, if we want to translate into string theory, expansion in large k for fixed lambda also translates into 1 over n. So there will be 1 over n terms contained in this just semiclassical expansion of membrane observables. So that means that using membrane semiclassics, we can capture 1 over n corrections from the point of view of string theory, which corresponds to this BGM theory. So then the main question is whether we can actually extract some useful information for quantizing membranes. And in fact, we wrote several recent papers which are examples where various observables in various theories, well, mostly this ABJM theory, but also 2,0 theory, six-dimensional theory, can be captured by quantizing, semiclassical quantizing membranes. So example which I will discuss is half BPS supersymmetric Wilson loop in ABJM theory. It's essentially can be reproduced, the leading localization result can be reproduced by quantizing M2 brane. So this half BPS Wilson loop, it means it's a circle, Wilson loop defined by a circle. So in the string context, that's a circle at the boundary of ADS5, for example, or ADS4, and you have a minimal surface ADS2 ended on this circle, stretched in ADS direction. In the case of membrane, the analogous surface is ADS2 times S1, where S1 is wrapping 11 dimensional over the over 11 dimensions. So it's a three surface that with this topology, with this shape. So it's essentially M2 brane probe intersecting the boundary of ADS4, which is multiple M2 branes. And this is half BPS kind of intersection, and that's why this is half BPS observable. So then we can compute M2 brane partition function, expanding in this large tension, and then match to what is known from localization. So let me recall what we actually know about similar computation in the case of Super-Yang-Mills theory. So in Super-Yang-Mills theory, Wilson loop is defined like path of the exponent of which is coupled to gauge field and scalar in particular way. This is half BPS Wilson loop, and its expectation value can be computed exactly using localization, using essentially Gaussian matrix model. And the result is expressed in terms of Laguerre polynomial. So it's explicit depends on Yang-Mills and N. So here you don't need to take any limits, we just exact result. But if we expanded large N and fixed lambda, we get expression which looks like exponent of square root of lambda, and then there is a prefactor. And this expression will have string theory interpretations from at large lambda. It will be action of string, the string action, and this will be kind of fluctuation determinants of string fluctuating near this minimal ADS2 surface. So in ABJM theory, similar operator can also be computed from localization, though here this localization story is more complicated. But the end result is instead of Laguerre polynomial, what one finds is some ratio of Airy function. So the localization result for Wilson loop in ABJM theory is exact function of K and N, a particular function. So you see here K appears and N appears explicitly, and they can be fixed. They can be any. Well, this expression actually is valid for K bigger than 2. So for K equal 1, clearly there is some problem here, and also for K equal 2. But for K bigger than 2, this applies. So M theory regime corresponds to large N at fixed K, and then you can work out how this function becomes at large N expansion. And that's explicit expression. So what you see here is this 1 over sine prefactor exponent, which will turn out to be action of membrane wrapped on ADS2 times S1. The prefactor will come from fluctuations of membrane near that surface. And then there are subleading terms, 1 over square root of N. So that should have interpretation of 2 loop or 1 over membrane tension expansion. Now, same function expanded in string regime when N and K are bigger than 1 with lambda fixed. So N over K fixed. That's how it looks like. So I kept sign here not expandable. Lambda over N is still small because N is large, but this is still kept as is. But if you take this expansion, what happens is that this sign gives you N over lambda here as a prefactor, and the rest are subleading terms. So interpretation, we can actually compare what we get in ADS5, S5, and ADS4 CP3 case, so in this Young-Mills and ABJM, comparing the two, how the two parameters are defined, how string couplings are defined, how tensions are defined, we find quite universal, quite similar expansions. So from string theory point of view, what we do, we have a boundary of space, ADS4 or ADS5, and we have minimal surface of a string, which is ADS2, ending on a circle, and then a Wilson loop is captured by string partition function on a disk. So on a disk means 1 over G string as a prefactor. So that disk topology gives you 1 power of string coupling. And both Wilson loops happen to have the same leading terms up to the numerical coefficient in the two cases. So this universal form actually comes out of the fact that the exponent is defined by the corresponding string action, which is same in ADS4, ADS5. It has the same just a volume of ADS2, and the prefactors are also kind of universal, which comes from the fact that fluctuation determinants have similar structure in both cases, ADS4 or ADS5. It's just fluctuations of string in these spaces. And in fact, one can argue that the general prediction of string side, how the dependence on string coupling and string tension should be at higher genera, it should be just this combination to leading order in string tension, expanding in large tension and expanding in string coupling. It should be a classical contribution of classical action, then corrections in string coupling divided by square root of t. So H here is a genus of a surface. So if it's H equal 0, this is square root of t over G string, which is disk. And then there is a disk plus 1 handle, 2 handles, etc. corrections. So this structure just kind of comes from the form of Green-Schwarz perturbation theory near this minimal surface. But remarkably, that's exactly what you get from this Laguerre polynomial from localization. Just rewriting this as expansion at large lambda and large n, the leading terms match this prediction. So the parameter of expansion is lambda and 3/4 over n. It's exactly this G string over square root of tension, which appears here. So comparing these two, you see the same. So localization tells us the coefficient, and the explicit value of these coefficients are just some particular function of H of the genus of this label, which gives sums, gives the labels the summons here, but which we don't know how to compute from string side, apart from disk contribution. But from localization, we know them exactly, and remarkably, one can actually sum up all terms at leading order in large n, but to leading order and string coupling. So ignoring subleading corrections at each genus, at the reach value of coupling, at each genus, you expand at large tension and ignore these subleading terms, then all these leading coefficients are such that, from localization, that they exponentiate. So all these leading terms sum up into exponent of H, where H, well, W1 is just the one loop to contribution, just this term. But all higher loops give exponent of H, where H is this combination, just G squared string over tension with coefficient pi over 12. So that's what follows from localization or in ADS5 in N equal 4 Young-Mills theory. That's the prediction for string theory, that all loops can be resummed into this kind of handle operator inserted on a disk. But what's the analog of that in ABJM theory? And it turns out the analog of that is 1 over sine function, not exponent, but this 1 over sine, because that's exactly what we saw in this localization result before. So I'll just show it again, and then I'll explain how that comes out. So this expression, this 1 over sine, happens to be the analog of this resummed exponent in N equal 4 theory. So in general, what we should expect for how BPS Wilson loop in ABJM theory, we have a classical action, one loop correction, then subleading terms in 1 over tension, then two loop, one handle insertion again, subleading terms, and etc. So a localization prediction is that all these leading terms, so ignoring subleading terms, should sum up into the 1 over sine. So 2 pi over k is exactly this G string over square root of tension. So just writing in terms of lambda and n, etc. So this 1 over sine actually give us one loop term plus two loop term plus three loop term from string theory point of view. So in that sense, this 1 over sine simple function resums all leading at large tension contributions from all high genera. And this 1 over sine can be reproduced from membrane very simple, well, relatively simply, just as one loop correction from doing semiclassics for membrane wrapped on this ADS2S1 surface from in 11-dimensional theory. So we put membrane in ADS4 times S7 over ZK, consider this membrane wrapped on this minimal surface, and find classical action, which happens to be the same as the action which appeared in string theory, and then do one loop, then look at fluctuations. And the fluctuations form towers of modes, Kaluza-Klein modes, if we expand in S1. So we fix static gauge. Static gauge means that ADS2 coordinates in target space are identified with sigma 0, sigma 1 coordinates on the membrane, and sigma 2 coordinate of membrane is identified with 11-dimensional circle. So then we end up with 8 plus 8 remaining transverse fluctuations, and there are 8 bosons, 8 fermions, and their masses are related to their masses are given by in terms of n squared over r squared, where r is 11-dimensional circle, and here it's this 11-dimensional circle is 1 over k, so the masses go as n squared over k squared. So explicit formulas have some shifts, but important point is that they just are given in terms of this n times k. So string theory limit is when k goes to infinity, a large k, then modes with n not equal to 0, they decouple effectively. They become very heavy and you can integrate them out. So you will end up with string theory in ADS for CP3. But in general, if you keep them, then you get information about string coupling dependence. So semiclassics of this membrane is given by classical action, exponent of classical action, one loop determinants. And these one loop determinants are just product of all this Kaluza-Klein index n, or this Fourier mode of S1 extra S1, all of these combinations of determinants, which are determinants in 2 dimensions now, because we spend it in Fourier modes, determinants in ADS2. Yeah. So what remains is just to find these determinants in ADS2 with particular masses, and this is straightforward with known technology. So what you end up with is very simple expression. So there are lots of cancellations due to supersymmetry, and one loop correction is just logarithm of this combination, which you need to define it with zeta function. There are power divergences, but that's like usual determinant of the one-dimensional harmonic oscillator or one-dimensional path integral for a particle. So with usual zeta function regularization, what you end up with is this sum, and this is just reproduces 1 over sine 2 pi over k. So the bottom line is the one loop correction membrane theory reproduces this leading prefactor in localization result, which is leading Lagen term for fixed k, and that resums all higher loop string corrections from in string theory at large string tension. So then one could ask about subleading terms, and I already mentioned that localization result predicts this 1 over square root of n term, which rewritten in terms of membrane tension is a 1 over membrane tension, T2. So that should be 2 loop term in membrane perturbation theory, and its localization says it's finite term, it has a very specific structure. So doing this computation in membrane is complicated, but probably it's doable, but it's just technically very involved. So it would be remarkable to reproduce this term from two-loop membrane computation. In fact, this indicates that membrane perturbation theory should be well defined, because if we believe in this ADS-CFT duality, we should be able to match these subleading terms. In fact, these two-loop computations were done in Green-Schwarz string, which is also formally not randomizable by power counting. And it turns out that this Green-Schwarz computation gives finite two-loop result, both in ADS-5S5 and ADS-4CP3. And the reason for that is effectively, in string theory, there is extra, well, the string theory in this space are integrable. So there are high symmetries which tell you how to define high loop corrections, even if theory is formally non-randomizable. Two-dimensional theory is formally not randomizable. So that's analogous to what happens in this TT bar story, where you have formally non-randomizable theory, but you may define higher orders in perturbation theory, insisting that you preserve integrability, quantum integrability at the quantum level. So something like that may happen in membrane theory, or maybe there are hidden symmetries which define this theory at higher loops. So that's what localization seems to indicate. If we believe this.
Just the precision, yeah. When you talk, yeah, that's clear. But from the you mean considering this irrelevant flows like TT bar deformations from the ABJM side, or
No. TT bar here is irrelevant, because TT bar is not going to work. So formally, the TT bar and integrability are connected only in 2 dimensions. So high dimensional. I was just drawing an analogy. I'm not saying TT bar applies to 3-dimensional membrane.
Yeah, exactly, because this is an integral deformation, but this is like an integral perturbation to.
Yeah. So here it's not in. This is not integrability. It should be something else, and it should be related to a large amount of supersymmetry.
Yeah, definitely. This is what I'm making precise, because you go beyond the planar limit. So integrability should not play really a role here.
Yeah. No, that's definitely so. At least we don't know what's the analog, what could be the analog of integrability in this story. Yeah.
So,
but again, it's a very close analogy between what happens in string theory and here. So it suggests that if Green-Schwarz action is well defined, the reason for that is integrability. But here it also should be well defined to match localization result. But what is the analog of integrability? It's not clear. Anyway, so let me quickly. I think I have only a few minutes left. So, so if we believe that, so this story seems to indicate. Well, this is what. Let me stress that it's highly non-trivial and quite remarkable that just doing this one-loop computation membrane theory, you reproduce localization result on gauge side. So it's a strong indication that first it's a check of ADS-CFT in this case, but also it's indication that membrane theory should be taken seriously. So then we can say, okay, so let's consider now examples where we don't have localization predictions, but localization results on gauge side, but we can actually use membrane perturbation theory beyond leading node in large N and make some predictions of how, say, anomalous dimensions of non-BPS operators should be beyond large N in ABJM theory. Doing what we usually do in string theory in ADS-5S5, namely taking some classical solution of string with large spin or large angular momentum and computing its energy, and then computing expansion in semiclassical expansion large string tension. So we can do the same for membranes. For strings, it was done for, say, for ADS4 at CP3, you can consider semiclassical strings, but then you can generalize them to membranes, corresponding membranes in 11 dimensions. So membrane is wrapped on 11-dimensional circle, so you essentially take string world sheet and add extra S1. Membrane is wrapped in this S1, but in ADS4 CP3, it will be just the same minimal surface or analogous minimal surface, depending on which solution. So for each string, semiclassical string or rotating string in ADS4 CP3, there will be corresponding membrane wrapped on SS1. And what we can do, we can then compute subleading terms in anomalous dimension of this dual cage theory operators using not strings but membrane and doing one loop computation membrane. So that can be done quite explicitly for cusp anomalous dimension ABJM theory. So it's again a long operator with large spin, and we look at coefficient of log s in its expansion. And we try to compute this function lambda n, now not in string theory, but rather in 11-dimensional theory. So that's the space. We consider analog of folded string. So it's a membrane which kind of folded string expanded in one extra S1 direction, and its classical solution for large spin. It's a very long string which reaches the boundary of ADS4, or long membrane in this case, and it propagates and moves in this space. So one can write explicitly how this action looks like, as we discussed. You can compute classical action of this string. You reproduce leading term in this f function. Then we can look at one loop fluctuation. And that can be done quite explicitly, similar to what I described for Wilson loop. One can compute fluctuations, their masses, and compute one loop correction to the energy of this membrane. So it's just given by, in this long string limit, is just given by some two-dimensional integral. Because we're looking at energy, so it's homogeneous in time. And this integral is it's an integral plus sum of a Kaluza-Klein modes, better than my sum. Yeah, sum is here. So this would be like a zero mode contribution of string modes, and these are Kaluza-Klein modes on this two-dimensional surface. So the masses again goes k times n, or n squared over radius of 11 dimension. And doing this sum, doing this integral, and for the string modes, you get -5 over log 2. That's what one finds in ADS4 CP3 theory. That's a leading correction to the leading one loop string correction to the classical square root of lambda behavior of this cusp anomalous dimension. And then there are higher loop string corrections. But in the case of membrane, similar analogous computation will give us, we need to integrate this summons of this sum of a Kaluza-Klein modes, and I'll just claim what is the result. So the correction which we get will be expanded large K. That's how it will look like. It's just a series of terms in 1 over K. They come from just this integral, which is straightforward to analyze. And these coefficients, as you see, is just zeta function. So it's sum over m, or yeah. So it's sum over m. Probably there's some what did I do here? I'm not sure. But the end result is just coefficients. They're just sum of zeta functions of 2m. It should be m and n interchange here, I think. I'm not sure what happened. But yeah, so the bottom line is that this correction to the cusp anomalous dimension, which was here. Now it's a leading term is just classical, and then there are f1 of k is function of this level k. So it goes as 1 over k squared, 1 over k4, etc. So that leading term gives prediction about for the non-planar correction on string side. So the conclusion is that at weak coupling, this cusp anomalous dimension non-planar correction goes as lambda 4 over n squared, but membrane prediction at strong coupling, so again that should be lambda bigger than 1, not less than 1. It should go as lambda squared over n squared. So that's a prediction for membrane. So we don't know what to compare it, but So this coefficient of 1 over n squared is function of lambda, which interpolates between this expression at weak coupling and this expression in strong coupling. So, so that's the use of this membrane perturbation theory. So in general, that's what we expect to find. We have classical term, one loop term, two loop term, etc. And this f of k, that's what we computed, this leading term, and it sums up all leading contribution at large lambda at each order in 1 over n, or loop or genus expansion on string side. Subleading terms will be determined by two-loop membrane computation, which is more challenging. And similar story can be repeated for other classical solutions in ADS. We looked at, for example, M2 brane with two spins, and what one finds is this is a short operator now for small j. It's due to the operator which is built out of two scalars of ABJM theory in power j, where j can be interpolated to small values. So that's a non-BPS operator, small kind of short operator, and its dimension at large lambda goes as fourth root of lambda. The lambda here is this lambda. It's fourth root of lambda, square root of j. Square root of j is the usual Regia behavior, like in string theory, you have square root of spin. But then there are corrections to that expression and a strong at large lambda. And that's the first line is string result, which was partly known, but then there are corrections at 1 over k squared. And that's what we computed, this 1 over k squared correction, which will be 1 over n correction from the ABJM side. So that's what is written here. It's lambda squared over n squared. So again, it scales as lambda squared over n squared. So that's the message, that non-planar corrections go like this. And one can also look at long string limit, but again, you will have 1 over k squared correction. So the conclusion is that there is some evidence that, first I presented evidence that matching with quantizing M2 brane semiclassically matches localization prediction for Wilson loop. And so that suggests that we should trust this M2 brane perturbation theory. And one could apply it to various other cases, in particular to computing index, corrections to index in 2,0 theory. One could go beyond localization, trying to compute subleading non-planar corrections to the dimensions of ABJM operators due to spinning strings and membranes, getting this prediction that these non-planar corrections would scale as lambda squared n squared at large n and large lambda. So that's prediction for string or torus contribution from the ADS4 CP3 string theory. And there are many open questions. As I mentioned already, there should be some presumably hidden symmetry in M2 brane theory, which should constrain loop corrections to analogous to what happens in Green-Schwarz string. The ways to detect this is not completely clear, but we tried to compute a matrix of brane excitations. Just like in string theory, you can study a matrix of fluctuations on a string, and that actually indicates, its properties indicate integrability, like factorization of two-dimensional matrix. So here is three-dimensional matrix. Here there is integrability is not visible, but we hope, in fact, the S matrix has rather peculiar structure, so it may be telling us something. I already mentioned also that membrane theory somehow resounds string perturbation theory. Semiclassical membrane already captures loops, string loops in the sense of string high genera through dependence on 11-dimensional radius or 11-dimensional background, which encodes dimension of string coupling. So that's quite remarkable and suggests that maybe we can indeed resum string perturbation theories effectively by replacing usual classical string action by non-local action, which from membrane theory point of view will come out of integrating all these Kaluza-Klein modes, massive modes, getting effective non-local two-dimensional theory. Yeah, I guess I stop here. Maybe it's worth emphasizing that membranes in ABJM theory give us something which we don't have so far in equal 4 theory. So in equal 4 supermembrane theory, which is dual to ADS5S5, we don't have ABJM theory. We don't have some other theory which describes some other way to describe what happens at strong string coupling. So we don't have analogous some D-brane probe computation of this 1/n correction so far. There is, if you have many strings, like if you consider strings in high representations, you do have effective description in terms of D3 branes, but there are various puzzles with this story, and it's not analogous to what I was describing in terms of M2 brane. So that remains a kind of interesting challenge. Why, what is the analog of this membrane computations in the context of N=4 theory? So thank you for your attention. I guess I stop here. I will run over.
Yeah, very good talk. Yeah, let's thank the speaker.
Sorry?
Yeah, let me see if there are any questions.
Yeah.
Okay. People think. I can pose at least one. In respect to this pure phase factorizable S matrix.
Yes.
Like starting like S matrix excitations from the branes. This study, it is not S matrix which is associated to the ADS4 background, right? So because from the integrability of S matrix ADS5 and the cross S5 and the ADS4 CP3 from the group theoretic approach, they are not too far. But what you are looking at, this is like in the string on flat space, right? So this is different.
Yes. So let me say more clearly. So let's start from the beginning. So consider Nambu action and expand it near long string. So consider very long string, fixed static gauge. So your Nambu action will be like determinant of flat metric plus dx. You expand in the dx, which are transverse fluctuation of a string. And you get an action which is like dx plus dx squared, etc. So dx squared, this would be this TT bar deformation effectively. So now we can scatter these axes and compute this matrix for scattering of axes. And these axes are massless. So that will give this massless S matrix still well defined because there's a derivative interactions. And this S matrix happened to be, which was discussed by Dubovsky et al. In particular, that S matrix is pure phase. It's factorizable, it's just a pure phase. And if you look at the corresponding TBA equations, it will reproduce free string spectrum. So this pure phase is related to the fact that this string theory is actually free fields theory, and its spectrum is known explicitly.
Yeah.
So it's just a equivalent way of saying that if you quantize conformal gauge, you know how to find string spectrum explicitly. But if you can quantize in static gauge, you'll need to, for example, you can use this TBA approach or integrability approach to compute string energies.
Yeah, sure.
So you can do the same computation in membrane theory now. Supposing membrane is just flat membrane, flat two-dimensional 1 + 1 dimensional surface times S1. Expand in this S1 direction in Akaly-Tsetlin modes, and then consider scattering of just string excitations, just those which are massless modes. In the loop, you will have all Akaly-Tsetlin modes running. And it turns out that the result which you get is also integrable. But if you consider one of the massive modes on the external lines, so if you include external lines as states on external lines, which will be massive, now the corresponding S matrix is no longer factorizable. So if you keep all these, so another way of saying this, you have effective two-dimensional theory of a few massless modes plus infinite tower of massive modes. So this whole theory, which will be equivalent to membrane theory on a circle, it will not be integral. That's what we found.
Because of this, the KK tower is exactly living on this, so these massive excitations are on the circle.
Yeah, yes. Well, because the original theory is three-dimensional, you just compactify an S1.
Yeah.
But it's still non-trivial. You can actually construct integrable theory with infinite number of modes by doing TT-bar deformation. So if you do TT-bar deformation of free massless modes plus free massive modes. Just take this infinite set, consider its stress tensor, and do TT-bar, you'll get integrable S matrix. But membrane theory is not that. So that's also what we discussed in our paper with Jonas Seibel. So membrane theory, expanding membrane action, you're not getting this TT-bar of just these Kaluza-Klein modes stress tensor. So that's not hard to understand why, but it's just a different structure of the action.
Yeah.
So what is not commuting is expanding its dx and compactifying the circle. Assuming membrane has cylindrical form. That's the difference. So anyway, these are details, but the bottom line is that there is no normal integrability in membrane action compactifying S1.
Yeah, I understand. But do you, when you say like you have certain hidden symmetry, do you have like any?
Yeah, this is just pure conjecture. Yes, so there might be something else which kind of tells you maybe it's maybe it's just extended supersymmetry, but it's a good analogy would be say a supergravity. So whatever four-dimensional supergravity is not renormalizable by index. It may be finite to some 3 loops, but at higher loops it's not finite. But what that really means is you'll get divergences, and a priori you would say, okay, I will need infinite number of parameters to define this theory. I need to specify coefficients of all these higher derivative terms in the effective action of supergravity. But it might be that there is some symmetry which we are not aware of, which actually constrains these coefficients in a very specific way. So there will be some prescription of what you need to do at each loop order, how you should subtract these divergences.
Yeah,
they should be very to preserve they should be subtracted in a very specific way, or equivalently, some counter term should be added in a specific way to define theory which will have this hidden symmetry at a quantum level. So that's analogous to this TT-bar in 2 dimensions, but analogy of this analogous mechanism in high dimension, we don't know. So that's a pure conjecture that maybe there is some.
Yeah, thank you. And no further questions, and probably let's thank the speaker again.
Thank you very much for attention. Yeah, thank you. So I can